Alright, there, welcome back to thinktankonlinelearning. So in this video, we're going to look at Excel loaded members. We're going to look at statistical internet problems. So I've solved this question using another method, and in this case, I'm going to show you how to use a step-by-step stiffness test method. Okay, so what we're going to do, I'm going to read the question first. A tube is fitted around the solid aluminium cylinder is shown below. The assembly is compressed between the rigid plates by central applied forces. So we have some forces right here, compressive forces. The aluminium cylinder is 70 millimeters, that's the diameter, and the steel is an inside diameter of 80 millimeters and outside diameter of 100 millimeters. If the force which is being applied is 240 kilonewtons, want to find the stress in the steel and the stress in the aluminium. So to those who have been supporting us, I want to thank you very much. I want to take this moment to appreciate you. You have been supporting us through comments, through liking and subscribing. So today is the day thinktankonlinelearning is 2,000 subscribers. So I want to thank my partner, Bright Mgoa. Without wasting time, let's get into work. So before doing anything, first of all, we have to write this numerical data. We have to write everything that we're given. So I've already done that. We have the numerical data, we have the force, the diameter, we have the interior diameter of the steel and the outside diameter of the steel. We also have the Young modulus of the steel, Young modulus of the aluminium, and we have the length, which is L. And what I've already done is that I've calculated the area. And if you look at the cross section of a diagram, we're going to see that we have the inner diameter, which is the diameter of the aluminium, which is 70 millimeters, and also we have a thickness or area of the steel. So what I've done, I've calculated the area. So the area of the aluminium is because it's just the core, so I'm going to say pi radius squared. In this case, I've used the diameter, that's why I've divided by 4 and squared it. And to calculate the area of the steel, what I've done is that I've subtracted the outside diameter minus the inner diameter, and you have to square them. And after that, I've calculated the area. And the other thing that you have to do, since we are dealing in meters, and as you can see, are given our Young modulus in gigapascal. So 1 millimeter is equals to 1 times 10 to the power negative 3 meters. So that means if you find the area, that means we're going to square the millimeters and we're going to multiply that by 10 to the power negative 6. So what I'm going to do, I'm going to follow these steps. So the steps that we're going to follow is that we're going to draw a free body diagram first, and we're going to write the equation of static equilibrium, and we're going to relate the structure and set one of the unknowns and remove it from the structure. We're going to load the structure with exterior force and determine the displacement due to that force. And after that, we're going to load the structure of the redundant and calculate the displacement due to the redundant force. And after that, we're going to use compatibility equation and find the unknown. Okay, so let's first start by drawing a free body diagram. So what we have a force of 240 newtons, and that means we're going to have a reaction from Newton's third law of motion. And the other thing that we're going to do when calculating stress, we just take the section. So either we're going to take the left section or going to take the right section, but I'm going to choose the right section here. So what we're going to do, let's choose the right section, and we're going to resolve it along the x-axis, and we're going to take the right side as the positive. Okay, so you have to make sure I'm writing this equation and resolving, because if you make an error in resolving, you get a wrong answer, especially when you're dealing with this type of problems. We have two metals here, so we have the aluminium and we have the steel. So don't make an error. Some people may treat this as bars, and you have 1, 2, 3 metals, and unfortunately that is wrong. Why? Because you know the steel is just covering the whole steel or the whole rod. So that means we only have two. We have the core and we have the outside. So let's resolve. So what we're going to say, since I've said going this one is going this direction is going to be positive, that means we're going to have R here, which is going to be positive. But since F is opposite, it's going to be minus F, and therefore that we're going to get 0. But let's take a closer look at R. We know that R is sum of the force that is being exerted by the aluminium and the force that is being exerted by the steel. So it's going to be FA plus FS, and that minus F, that should give us 0, meaning FA plus FS can give us F, and we're going to call this equation number 1. And let's move on. We've drawn the free body diagram and we've written the equation of static equilibrium. So the next stage is to release the structure and set one of the unknowns and remove it from the structure. Okay, so we're going to choose the one that we don't need. Okay, so we have the steel and we have the aluminium. So I'm going to remove the core. So let's do that. So if we remove the core, as you can see, we're only going to be left with the steel. And I think I've explained it why we don't have a steel, right? It's just cylindrical, it's just cylindrical and just circular. So we're going to have one steel. So that means we have removed the aluminium. So our force is still acting. We have removed the aluminium and our force is still acting. And know that our force is 240 kilonewtons, and we have a reaction here, and that reaction is going to be Fs. Okay, so from this I think we can agree that if we resolve, so this was step number 2 and this is step number 3, and we can agree from here that if we resolve, we know that Fs, which is positive, minus F, that is going to be the force, that should give us 0. Okay, and this means Fs is equal to F. Okay, but from our instructions we have to remove it from the structure. Then we're going to load the structure with the exterior force and determine the displacement due to that force. So what is the exterior force? The exterior force we've said is 240, so we've loaded it. Now it's time to determine the displacement due to that force. So know that the displacement is going to be equal to the force times the length times the area times the modulus. So here it's going to be the displacement due to the force. And what is going to be the force? So the force is going to be the displacement of the steel. It's going to be the force in the steel, which is Fs times the length of the steel times the cross-sectional area of the steel times the Young modulus of the steel. And from here, since we say that Fs is equal to F, so that means you can just write this as F, Ls, As, Es. And we say that S is just subscript for the steel. Okay, so I'm going to write this as equation number 2. Okay, then what we're going to do next, we have released it and we have loaded the structure with the exterior force. Now it's time to load the structure with the redundant and calculate the displacement due to that. So what I'm going to do, I'm going to add back the redundant, and we say the redundant was the aluminium, right? So this is the aluminium, and we have to remember from our free body diagram, we know that the reaction of the aluminium was going in this direction, opposing the compressive force. Okay, so this is Fa for the aluminium, and for the steel it was also going in this direction, Fs. So you have to make sure you don't confuse anything right here. Okay, some people may say no, the steel is not going in this direction. No, what we're going to do, we're using this superposition. What we're going to do, we're going to treat each force separately. So now we have treated the exterior force, and now we're going to treat the redundant force. So we're not going to change anything, because as you can see from here, we had a tensile force since the 240 kilonewtons was opposing, or it was compressing. So it's going to be a reaction, and that reaction is going to go in this direction for both metals, for the steel and the aluminium. Okay, so we've loaded it, and now what we need to do, remember, was to stopped. We're no longer talking about this force F. Why? Because we're treating one force at a time. So, and what we're going to do from our instructions, what we're going to find the displacement due to this force, due to the redundant. So we can write here. So now let's take a closer look at here. We're going to resolve. So that means if we resolve along the x-axis, we should get 0. So that means what we're going to have, we're going to say Fs plus Fa should give us 0, meaning Fa is going to be negative Fs. Okay, and now we're going to find the displacement due to the redundant. So the displacement of aluminium A due to the redundant force is going to be Fs. It's going to be the force, it's going to be Fa, the force being exerted by the aluminium times the length of the aluminium times the cross-sectional area of the aluminium times the Young modulus of the aluminium. And now we're going to go to the displacement of the steel due to the redundant. So it's going to be, the displacement is going to be F, and what is F? It is the force, which is going to be Fs times Ls divided by As times the Young modulus S, right? Okay, so this is what we have, and from here I think we have said that Fa is equal to negative Fs. So that means if you want to modify something right here, you can write it as, for Fs right here, you can write negative Fa. So it's going to be negative FA LS over AS ES. This is going to be the third equation. So now it's time to write the equation of compatibility, and that is going to be number, so we say this is stage number 4 and number 5 right here. And for number 6, we're going to write the equation of compatibility. So let me just write it here, equation of compatibility. So since this thing is rigid, we know that the change in length of the steel is going to be the change in length of the aluminum. So it's going to be the change of length of the steel should be equal change of length of the aluminum. And I'm going to call this equation number 4, right? Okay, so now let's solve these equations. We have 4 equations and we have 2 unknowns. Okay, so from here, from the equation of compatibility, let's look what is going to happen here. So you have to be careful again. Why? Because we're going to use a force relation, a force displacement relation right here. We know the 240 kilonewtons is going to compress the size of the steel, right? If we treat it separately, it's going to compress the size of the steel, and the force FA, or the force due to the redundant, is going to elongate it, right? It's going to lengthen it. So now I'm going to write the force displacement relation right here. Displacement relation, and remember we're resolving along the x-axis, taking the right side as the positive. So let's take a closer look. So what is going to be, we said the change in length of the steel should be equal to change in length of the aluminum, right? And on the steel, we're going to have a negative, since the F, or 240 kilonewtons, is going to shorten it. So it's going to be negative what? And we say this is the force, or this is the displacement due to that force. We're going to have negative F LS times AS ES. So this is the displacement due to the force, and this force is going to add it, as you can see. So I'm going to say plus, but unfortunately it already has a negative sign, and I've explained why it is negative sign. So I'm going to write minus FA LS divided by AS ES. And on the displacement of the aluminum, which is AES, sorry, it's going to be, the displacement of aluminum, we're good right here. It's going to be FA LA, and we're going to have AA EA. And some people may say, why didn't you include the aluminum here? We said you've removed it, and we're going to treat them separately. So from here, I think we can solve for FA, because as you can see, we have FA, we have FA, we have FA right here. Okay, so that means we can solve for A. So we're going to see that F LS AS ES, we have a negative sign right here. It's going to be FA LA over AA EA plus FA LS. We're going to have AS ES. And from our numerical data will say that LA and L are the same. Since it's just the same cylinder, the length is not changing. From here to here, it's 200. So I can divide both sides by LA by LA. Okay, and after doing that, we're going to factor out FA right here. Let's factor out FA. So we're going to have FA, and we're going to have 1 over AA EA plus 1 over AS ES, and this should give us negative F AS ES. Okay, and we have our values right here. So if we make FA such that the formula, it's going to be negative F divided by AS ES, or divided by this, which is going to be 1 over AA EA plus 1 over AS ES, right? Like this. And let's plug our values. For here we have negative 240 kilonewtons. That's going to be negative 240 times 10 to the power 3 newtons, right? Divided by, and area, that's going to be the area of the steel, which is going to be 900 pi square millimeters. We're going to change that to meters. It's going to be 900 times 10. This is modulus of the steel. Okay, so the steel, that is going to be 210 times 10 to the power 9, and that's going to be Newton per square meters, right? and we're going to divide that by 1 over, so the area of the aluminium is going to be 1225, that is 1225 pi times 10 to the power negative 6 meters squared. We're going to multiply that by the modulus of Young modulus, and that is going to be 70 times 10 to the power 9 Newton per square meters. And we're going to add plus 1 over area of the steel, that is going to be 900 pi times 10 to the power negative 6, and that's going to be meters squared times ES, modulus of elasticity, and that is 210 times 10 to the power 9 Newton per meter squared. And if we solve here, we're going to get, so if we are going to get negative 74.9 kilonewtons. But I think you know, when mechanics, so we have resolved going to the left to the right hand side. So if we have a negative, that means that force is 74.9 kilonewtons and it's compressive. We're going to move on to Fs. So Fs from equation number 1, you know that Fs is equal to F minus Fa. And what is F? And F is 240 kilonewtons. We're going to subtract 74.9 kilonewtons, and if we do that, we're going to get 165.1 kilonewtons. Okay, so now that we have Fs and we have Fa, you can now calculate the stresses. So we're going to start by stress in the steel is going to be Fs divided by As. Fs, which is 165.1 kilonewton, divided by the area, 900 pi times 10 to the power negative 6 meters squared. And if we do that, we're going to get 58.4 kilopascals, and the stress in the aluminium is going to be Fa divided by Aa. And Fa, the force, Fa is 74.9 kilonewton divided by, and by the area, which is 1225 pi times 10 to the power negative 6. And I'm taking this information for the numerical data, square meters. And if we do that, we're going to get 19.46 kilopascal. Okay, so on the displacement, what we're going to use this equation. So now for the displacement of S is going to be displacement of A. So for part 3, I'm going to write the displacement. I'm going to choose steel, and displacement is going to be F of the steel, force acting on the steel, Ls, length of the steel, times As, area of the steel, divided times, which is E, the modulus of the steel. So this is going to be for the force acting on the steel. Fa said is 165.1 kilonewtons. Now I'm going to change it to newtons, so we're going to be times 10 to the power 3 newtons. Now going to multiply this by the length. So the length is 200 millimeters. Changing that to meters is going to be 10 times 10 to the power negative 3. I'm going to divide that by the cross-sectional area, 900 pi times 10 to the power negative 6. Change that to square meters. Modulus of elasticity, 210 times 10 to the power 9 newtons per square meter. And if we do that, we're going to get 5.56 times 10 to the power negative 5 meters. That is going to be the change in length. Thank you for watching.